Hey guys, this is K.Sudharshan and I'm here to present information about Hall effect, transducers and magnetometers. So basically Hall effect. Hall effect is how the Hall effect sensor works. It is a working principle, and in a sense when a current carrying conductor is placed in a magnetic field oriented perpendicular to the current, there is a voltage generated perpendicular to both the current and the magnetic field, and we call this voltage the Hall voltage, and the effect is hence the Hall effect. It has been named after the scientist Edwin Hall. When we work with Hall effect, we can consider like a thin slab or a conductor through which when we pass a current through it, say I, there is an electron flow in this direction, of course, and let's say it has a carrier charge density of n. Now suppose I induce a magnetic field coming out of the board, say perpendicular to the board B. Alright, and this is going to, we know this is going to cause a drift in this direction because of the magnetic field, and let's say we can accredit this drift to a Hall voltage as such, called the Hall voltage, which occurs across this field, and let's say this thickness is D. Alright, so this VH can be accredited to the Hall voltage. So what I have to do right now is find an expression for the Hall voltage, right? So what we can do is write E times electric field due to the Hall voltage should be equal to E times Vd drift velocity times B, right? I'll cancel the E's out. We'll come back in later. EH can be written as VH by D. This is equal to Vd. Vd is given by J by Ne times B, right? J by Ne times B. J can be written as I by NEA times B, right? And sorry, this should be T, yeah. So VH should be equal to IB times NT times T. So you get VH is equal to IB and NED. Yeah, so basically VH, the Hall voltage, can be given as a function of current, the transverse current, the current that flows through the conductor initially, the magnetic field applied, carrier charge density, the charge value, and the thickness of the slab, right? Thickness is this thing, sorry. Yeah, the thickness of the slab. The Hall effect sensor basically works on the Hall effect, as the name suggests. So it is a transducer which you use to measure the magnetic field. You remember the voltage that we calculated across this region, across this thickness, as VH, right? That is going to be what we are going to measure, and it is going to be transverse to the direction of the current that we use to run the sensor, and the magnetic field perpendicular to this. The strength of the magnetic field can hence be measured by measuring the voltage. Basically, the formula that we used before to quantify the Hall voltage can be used to measure the magnetic field too. And as a circuit element, the Hall effect sensor is Hall effect transducer or sensor is represented by this diagram over here, and this is like an image of the Hall effect sensor. Some more intuitive information about the Hall effect sensors include the fact that, basically it needs to contain some type of semiconductor. We'll come on to the fact of why we use a semiconductor instead of a metal. Hall effect sensors are basically passive transducers. Passive transducers in the sense we needed a driving current to actually calculate the Hall voltage, right? I mean, we had to intake this current in. And the working of the sensor depends on the strength of the magnetic flux and the mobility of the carriers. So the magnetic flux, of course, comes out of this term in this thing. We wrote this as an EP. And basically the I by NE term can be kind of equated to some form of conductivity. And this conductivity gives an output. Conductivity is basically related to mobility of the charge carriers, right? And hence we can say the Hall voltage is going to be dependent on the conductivity and the conductivity and the magnetic flux intensity. This formula here is just like how we had derived before. We can basically see I is the feeder current, the current that is being fed to the Hall sensor outside. B is the strength of the magnetic field transfers to the current. Q0 is the carrier charge value, it is the magnitude of the charge, and n is the charge density, carrier charge density. N is a very important value, as we'll see in the next slide. D is the thickness of the slab that we are taking, or slab, or any sample that we are considering for the measuring the Hall voltage. Why semiconductor over metal? So we can see the VH value, and the value of carrier is inversely proportional to the carrier density, right? So I write VH as I B by capital M Q naught D, right? And you can see N is inversely proportional to VH, or VH is inversely proportional to N. And so materials with low carrier densities would be more prominently showing Hall effect. The value of the Hall voltage would be greater in the cases where the carrier concentration is very less. So basically metals have high carrier densities and hence show lower values of Hall voltages. Comparatively, semiconductors would have moderately lower carrier densities and hence they can show better Hall voltages, and in the sense are more feasible for us to detect the voltage as such. And in types of Hall effect sensors, now we'll go through a bit of some of the types of the Hall effect sensors, or the way in which Hall effect sensors can be classified. So analog Hall effect sensors and digital output Hall effect sensors is one way in which you can classify it. There is only one difference between the analog and the digital. The output obtained by the digital is combined with a Schmidt trigger over here. As we can see, there is a Schmidt trigger over here that is going to act like a switch that is going to make it a digital output compared to analog output. Yep. You can see there is the advantages of each of these. There is stable behavior in noisy environment as it is in most analog environments, and large voltage range to operate in. While the digital output is known as the bilevel Hall effect sensor because digital. Yep. And the design is the same as analog except for the addition of the Schmidt trigger. More sensitive. The other way to classify transducers would be in terms of their construction. So basically, bulk transducers. Bulk transducers are basically, in the sense they are made of bulk materials as such. They are made of bulk materials. Matlab they have higher volume. They look more like a cube. You can say they look like a cube. And the advantages of this is that you can have great deal of choice in selecting the materials. And large size of transducers as such, as I said, they have bulkier volume, and large size of transducers result in lower impedance levels. There's going to be lower impedance / resistance levels, and consequently lower noise levels than other methods. This is kind of an intuitive solution. Below I have given the values of sensitivity at recommended bias current and sensitivity current reference. I'll come back to these terms later in the other slides. You'll get to see a comparative idea of how it works with the other types of transducers. Just take a note of these values so that you can compare it to the other results. Thin film transducers. Thin film transducers are basically thin films of semiconductor condensed on ceramic substrate with metal contacts attached to it. So this is how it looks, and the cross section looks like this. And you can look at the sensitivity. Take a look at the sensitivity values given over here and compare it to the ones on the previous slides as such, right? So thin film transducers are of course small in size. They are small in size as such, and hence more versatile. I think they can be used in several components that pretty much were used in phones before. There is a flexibility in material selection, and thin Hall effect transducers provide more signal for less bias current. Now, without going into detail, let me just say integrated Hall transducers are basically Hall effect transducers but embedded on silicon chips. So they are made to be integrated with other IC elements as such. And for a comparative idea, we have given the characteristic sensitivity readings for a general integrated Hall transducer over here. So that you can compare it with the other values. I guess all three of these transducers have been, the readings have been taken at Bell Labs. Other way in which we can classify Hall effect sensors are based on the geometry. We can go in detail for this later, but we want to move ahead to the applications of the Hall effect sensor as such. So basically, we have given the value of resistance at a given temperature and magnetic field. At zero field, the zero field resistance is given over here. There is a sensitivity given over here with respect to temperature, I guess. and then the offset drift. So we have given several parameters regarding construction of Hall effect sensors, and the different types of Hall effect sensors have also been given. I have provided the links to read about the geometry and shapes as such in the reference section, which you can check out later. All right. Moving on to applications, the most obvious application of a Hall effect sensor is going to be the magnetic to electric transducer, basically measuring the magnetic field as such. So we can use this to measure the magnetic field. You would say this is basically working like a compass, right? So we'll look at compasses later. So basically this is going to be used to measure, used as a compass. The other thing you can do is to measure displacement, the measurement of AC or DC current. Rotary encoders. Rotary encoders is something that we have seen before. Rotary encoders can be used. It can be used as counters, basically. Encoded switches. Hall effect sensors are very good switches. They can be and this are pretty much related. Open close detection of laptop flip screen. So basically, the fact to check if your laptop is open or closed can be used. Is practically a switch, right? And then there is a flow meter. So basically, now that I mentioned flow meters, I would also mention speed detection. So basically, we can use this thing, Hall effect sensor, to detect speed as such, more like a rotor. Flow meters is basically speed detection, but when we have like water, say, flowing down, and there's like something like a pedal over here, the water pushes the pedal down, and we say let's say these are magnetized, and if the magnetic flux linkage with respect to the Hall effect sensor can be noted down and the readings taken, I guess. This is probably how a flow meter would work with the help of Hall effect sensors. Okay, let's bring the focus on Hall effect sensors as magnetometers. So Hall effect sensors can measure a wide range of magnetic fields that are sensitive to both the magnetic orientation of the field. As we have read before, Hall effect sensors are sensitive to high ranges of magnetic field. And they offer high speed operation as such. They are like when you see, like, remember using a compass as such, the time it takes for a compass to orient in the right direction is pretty significant, right? And in comparison, the Hall effect sensor is going to give you the answers instantaneously, and they can work in wide temperature ranges. As I've seen, they work from like about 0.15 Kelvin to huge ranges, like in ranges of 1000 kelvins, like huge temperature ranges as such. And here, like, we have the image of a Hall effect gauge meter. Basically, gauge meter, in the sense, it reads the strength of the magnetic field here, right? Now let's talk about other magnetometers. So Hall effect magnetometers are very good options to be used in like portable versions. So probably Hall effect magnetometers are very widely prevalent in your phones. There is a video recording showing how it is being used in phones. Basically, if you have any compass application on your phone, it basically uses a Hall effect transducer. Basically to detect orientation. They can be coupled with accelerometers and gyroscopes to actually give you a sense of rotation and whatnot. But for laboratory purposes, we need more advanced techniques to measure the magnetic field intensity. So instead of using Hall effect magnetometers, there are highly advanced techniques such as the squid over here. You can actually see the squid at working if you go to a cold physics laboratory or a solid state physics laboratory. You can go to the instrumentation to check this out. I have MPMS squid. Optical magnetometry, torque magnetometry, and vibrating sample magnetometry are other techniques that can be used. So basically, these are laboratory techniques. The Hall effect magnetometer is mostly a survey technique of using measuring magnetic field and its orientation.
was invented over 2000 years ago and were made of lodestone, a naturally occurring magnet. During hundreds of years, compass changed shapes and sizes, but for most modern applications, they are still considered as bulky and slow. This is a 3-axis digital compass known as magnetometer. It costs less than $2 and is much more fast and precise than a conventional compass. But how a magnet can be replaced by a little silicon chip? Well, physics has the answer. When electric current is flowing through an electric conductor, electrons generate their own magnetic field, and when external magnetic field comes in, it interferes with existing magnetic field of electrons and exerts a force on them. This force is known as Lorentz force, named after physicist Heinrich Lorentz. Then in 1879, Edwin Hall discovered that if a flat current carrying conductor is exposed to magnetic field, electrons accumulate on one side due to a Lorentz force. And because of uneven distribution of charge, if we connect a voltmeter to the conductor, voltage can be observed. And by observing the characteristics of voltage, such as its magnitude and whether it is positive or negative, magnitude or strength and direction of magnetic field can be determined. Hall effect sensors designed and modified especially to measure Earth's magnetic field are known as magnetometers. They are in a category of micro-electromechanical systems. They can be so small that size of an entire 3-axis magnetometer can be less than a couple of millimeters. That makes them perfect to embed in smartphones. Nowadays, magnetometers are used with other sensors such as gyroscopes and accelerometer with various sensor fusion algorithms to determine precise orientation. That makes them backbone of various virtual and augmented reality applications. But their most important use remains the same as was 2000 years ago, which is navigation, to give a sense of direction, to make sure we are always heading in right direction.
So basically given over here is like a video of the magnetometer on my phone working. I've used an app called Firefox to actually help me out. The Hall effect sensor is basically detecting the magnetic field in all 3 directions and the absolute magnetic field. And the graph over here basically shows the value of the magnetic field in all 3 directions. You can see the magnetic field around the y-axis is 0. That's because I'm holding my phone horizontally. And the magnetic field along the x-axis is pretty significant, equal and almost equal to the z-axis field. This is basically how inclinating compass, the compass navigator is used pretty much works, and it shows the declination and the azimuth of the magnetic field in magnetic field of the Earth. The absolute value, as you might notice, is not actually matching the Earth's magnetic field. That might be due to distortions or due to my altitude, the altitude from which I'm measuring the magnetic field. Slide 7 here. So basically we, beyond Hall effect transducers, Hall effect is pretty prevalent in other cases too. Like here is almost, here I would prefer to call this a Hall effect actuator as such. This is a HET or Hall effect thrusters created by Russian cosmologists first, and then headed on by JPL NASA. So it is pretty common instrument used in current space missions. I'll play the video and show a demonstration. Yep. I'll give a description of the video because there is no audio recording attached to it. So basically given over here is a Hall thruster demonstration. They're going to show how much thrust the Hall effect thruster is going to produce in comparison. Basically they'll label and show what each and every part is right now. Yep. So you can see the Hall thruster attached over there next to the aluminium target. And there's an external cathode. This is how a Hall effect thruster is usually set up, even in outer space. So basically there is going to be a flow of charges, electrons over here, which is going to be ionized by an very high electric field, and then a magnetic field applies a thrust to it, which is going to cause like these charged particles to flow out and provide a significant amount of thrust. You can see how that aluminum foil started moving about. Now, the University of Michigan is trying to produce even more strong Hall effect thrusters. Basically, they have demonstrated this summer. University of Michigan is trying to demonstrate even more stronger efficient Hall effect thrusters. So let's hope they work out. So I would like to, this brings us to the end of our presentation. I would like to give a note to my references first, and then head on to the summary. So basically, I have taken information from the following websites. If you want to read more about Hall effect sensors and Hall effect as such in general, you can head on to these. And moreover, beyond these, that you can check out Texas Instrumentation Archives. Like, I found a huge amount of information over there. Texas Instrumentation, and beyond that, you can click on my videos to actually check out more about Hall effect sensors as such and Hall effect thrusters. Before I end the presentation, I would like to give a summary of what's happening as such. So basically, we checked out so basically we checked out Hall effect and how it works. We saw Hall effect as the working principle of Hall effect sensors, of course, as working principle of sensors. We saw different designs and types of Hall effect sensors, or I would like to shorten it to HEIS. And beyond these, we saw magnetometers and how Hall effect sensors worked, and how Hall effect sensors worked as magnetometers. And we also saw other types of examples of magnetometers. Basically, magnetometers are more used as survey elements rather than laboratory elements. And laboratory elements have also been seen, like squids, which are like pretty prominent. Now, beyond magnetometers, we saw Hall effect thrusters. Basically, I would call this an actuator, but we'll see about that. And pretty much sums up what we have seen. So I guess you learned a lot from my presentation here. And if you have any suggestions, I would like you to contact me. Thank you.